I believe more people will be joining in, so I guess I'll get started. It is my great pleasure to introduce today's medallion speaker, Rob Nowak. Rob is a professor of electrical and computer engineering at the University of Washington, and his work has had a profound impact on foundational statistics and data science. Rob has co-authored numerous papers and book chapters on a large array of topics at the intersection of statistics, signal processing, and machine learning, with notable awards for his work, especially on algorithms for sparse estimation. But what we are most grateful to Rob for is his beer mapper app, which is an app that uses ML to help you find your ideal beer. So I invite you all to use his app, but only after we finish the talk, which today will be on neural networks. Let me paraphrase, past, present, and future. And before I hand it over to Rob today, let me tell you that we are all looking forward to a very interactive session. Feel free to interrupt at absolutely any time. We will be monitoring the chat screens. Please raise your hands. That's how you want to draw our attention, that you want to ask a question. The structure of this lecture will be a little different than others. It will have two parts, and while you are encouraged to ask questions during the first part, and genuinely encouraged to do so, there will be also ample opportunities after the first part to ask more questions, because we'll take a break, allowing especially for this question. Then we'll move on to the second part and more questions. And with that, I'd like to welcome Rob.
Awesome. Well, thanks for that great introduction. Thank you both for this invitation to speak today. It's a real honor. I've been an active participant in a few different research communities, as you mentioned, signal processing, machine learning, and also statistics. And I have to say, I think I may have learned the most from the statistics community over the years. And it's fun and special to be here talking about some of the things I've learned and trying to tell you all about it. So again, many thanks for organizing this and inviting me. And all I can say is the only downside is I'm totally bummed about not being able to be together in person with everybody, but hopefully this will be pretty good anyway. All right. So what I'm going to talk about today is what kinds of functions do neural networks learn? And to kind of get into this, I'll just kind of remind you that everybody's heard about all the amazing successes of deep learning in image classification, text translation, all sorts of game playing applications, robotics, and so forth. And this has really set off, tremendous excitement, not just in, research circles, but in popular press and the world around. We've gotten titles like this from the New York Times, The Great AI Awakening. Wall Street Journal had an article, AI is the New Electricity. So there's certainly a lot of excitement, probably a bit of hype too. But nonetheless, it's kind of been amazing how successful some of these deep learning systems, as they're called, have been in a variety of applications. And so just to kind of emphasize one of the points I want to get into today is we're going to talk about deep neural networks. We'll eventually get to deep neural networks. And there's a kind of general trend, and that is that bigger is better. And so here I'm kind of depicting what's going on in the case of image classification. This is kind of the goal here is to give a computer an image, and then the computer should be able to identify different objects in the image. And then on the right here, I'm showing how accuracy or performance behaves as a function of parameters. And so what you see over time is people are building larger and larger neural networks. Now we're into hundreds of millions of parameters. And as they keep growing and building these enormous complex models, the accuracy in these classification tasks is just steadily increasing. And so here I'm depicting a graphical representation of this so-called inception ResNet V2. It's each one of these little boxes, you could think of it as a kind of conventional little neural network. And so they're stacking all of these layers of neural networks together to build these incredible recognition systems. One of the important things to kind of note here is that we're really in this large P little n type of situation. These models typically have hundreds of times more parameters P than data points N. So they're over-parameterized is what the terminology typically used in machine learning. And so even though these models have more degrees of freedom than data points, they're still able to generalize and perform very well in these tasks. Here's just another depiction of this trend, starting all the way back with the earliest neural network called the perceptron in the late 50s, all the way forward to today. And this graph is sort of illustrating the increase in the complexity, size, and computing involved with neural networks. It was roughly doubling every 2 years in what they called the first era here. But then in the modern era, say in the past 10 years or so, we've seen a doubling every 3 months. And so these neural networks are getting enormous. The current leader, I believe, is GPT-3, which is a deep learning system that generates text. So you can ask it questions, interact with. I'm sure everybody's heard about it. And that involves about 175 billion tunable parameters. So these are incredible and to a large degree poorly understood from a mathematical perspective. So just to be clear, and we'll be going through this many times, so if you don't get everything in this one slide about the notation and so forth, we'll see it again in simpler forms and so forth. But what we're going to focus on are fully connected feed-forward neural networks, which consist of kind of a composition of affine linear transformations of the input, followed by a scalar kind of coordinate-wise nonlinearity, or activation function, as they call it. And those are also what are called the neurons here. So these orange nodes are the neurons. The layers here denote layers of this compositional structure. And so you have, again, affine transformations followed by coordinate-wise nonlinearities, and you just repeat this process. And the weights and these offsets, or biases, as they're called in these affine transformations, are all tunable parameters. Just another little bit of terminology that you may or may not be familiar with. People will talk about the width of a neural network. That basically just refers to the number of neurons in each layer of the neural network. And the layer is just the number of compositions involved in this function here. And that's called the depth. So they'll talk about the width and the depth of the neural network. And deep neural networks get their name from this idea of depth, many, many layers of these affine followed by coordinate-wise nonlinearities. Okay, so what do I want to talk about? I want to talk about or think about how we might be able to start understanding deep learning through the lens of mathematical statistics. And so just to kind of frame it in a very simple way, we have a neural network. It's got a bunch of parameters. We'll call those parameters theta. Those are the weights and biases or offsets in those affine transformations. Those are all tunable parameters. And so we have a function, a parametric function, f sub theta. The point is theta might be hundreds of millions of parameters in some cases. And what backpropagation algorithms do, backpropagation is basically just gradient descent, they're quote unquote training the neural network to fit a set of data using gradient descent to solve something like a ridge regularized sort of data fitting problem. So we might look at something like the sum of squared errors our model makes on our data points, plus a regularizer, which is just a ridge regularization of the neural network parameters. So that's a pretty standard learning objective that would be used in training neural networks. And so the question that I want to focus on in this lecture is, if theta hat's a solution to that optimization, then what properties does the function f sub theta hat have? And how do those functions that we learn from neural networks relate to more classical nonparametric methods that we know in statistics? So as Flori said, I'm going to divide this lecture into two parts. The first part, I'm going to look at univariate neural networks and single layer neural networks. So this is sort of the simplest setting. We can relate neural networks to many techniques that we're familiar with in nonparametric statistics. And then the second part, we're going to move to multivariate and deep neural network structures. This is where things really deviate quite a bit from classical methods. And we'll be discussing that in those two parts. And again, as Flori said, I really hope people can ask questions as we go. And especially, I'll pause after part one. It would be a logical place where people might have questions on that part of the talk, and then we can resume and move on to part two. And I just want to also mention that this is largely related to work with my really amazing graduate student, Rahul Pari. All right, so part one is univariate single layer neural networks. So what am I going to talk about here? I want to sort of highlight relationships between neural networks and some other really famous and classical techniques that I really like and I've used all the time in research and so forth. And so one is reproducing kernel Hilbert spaces. These are linear methods that effectively involve L2 regularization. And so one instantiation of this are the L2 Sobolev spaces. And there we have things like classical smoothing splines and truncated series estimators. And so I'm going to go back over smoothing splines and that sort of stuff because it's very related to what we're going to be talking about with neural networks. Another area that I was really involved with back in the 90s, especially, was wavelet representations and wavelet methods. Wavelet representations are great for all sorts of spaces, including the Sobolev spaces, but also bounded variation and Bezov spaces. And these wavelet methods involve nonlinear approximation and wavelet thresholding, which is, again, related to more of an L1 type of regularization. So the difference between the smoothing splines and RKHS methods and wavelet methods is really this difference between L2 and L1, and we'll see that theme come up a lot here. And then finally, what I'm going to connect all this to is neural networks, and it turns out these are also very naturally suited to bounded variation spaces. And again, when people train neural networks, they're using ridge regularization and gradient descent. And sort of surprisingly, that also leads to L1 regularization, even though we're using an L2 ridge regularization scheme. And I'll show you why that happens and what that means then for how neural networks fit into this picture relative to the classical methods like wavelets and smoothing splines. Okay, so to kind of contrast all three of these approaches, I want to look at two different function spaces. And one of the function spaces is going to be a familiar sort of Sobolev space, and the other is going to be a bounded variation space. So specifically, these function spaces are defined in terms of the second derivative of a function. So we're going to look at functions in L2 and then look at their second derivatives and either have their second derivatives being square integrable or absolutely integrable. Okay. And we're going to be thinking about these derivatives in a distributional sense, and you'll see why in a second. We're going to need to be able to deal with things like Dirac impulses and so forth. So these spaces nest. L2 contains everything. Then we have BV2, this bounded variation space, this L1 type of space, and then H2, the Sobolev space, is actually contained within that. And so here's an example of a function that's in the bounded variation space, but not in the Sobolev space. It's a continuous function that's smooth everywhere except at some corners. So this is in BV2, but not in H2. And if you take its second derivative, again, in a distributional sense, you'll just get a series of Dirac impulses. And those impulses live in this BV2 space, but do not live in H2. So that's one of the things that we can handle in BV2 that can't be handled with the Sobolev space. And the long story short, the thing that we're going to kind of conclude with in this first part of the talk is that all three methods, kernel methods or linear methods in general, wavelets, neural networks, can be optimal for learning in these Sobolev spaces, but the kernel methods are suboptimal for learning in bounded variation spaces, and we'll see why that is. Okay, so let's think about the Sobolev space problem. The natural way to frame this is to say, well, I want to find a function that fits my data, but I want it to have a small norm in the small Sobolev space or small semi-norm. So here's the Sobolev semi-norm. It's just the squared integral, the integral of the second derivative squared. So that's going to be our regularizer. And we know from classical work of Kimmeldorf and Wabe, one of my favorite colleagues here at UW-Madison, that the solution to this variational problem is a smoothing spline. And the coefficients in this smoothing spline representation are just the solution to a simple minimizing quadratic function of that form that you see there. And so because we have this quadratic regularizer in this minimization, the solution is linear in the data. So we could equivalently write that smoothing spline as some weights that depend on the new point X where we're evaluating that smoothing spline times the data Y. So it's just linear in the data Y, and so we call this a linear method. Now, what do we know about this statistically? If we have a set of data that are generated by some optimal regression function F star that's in this Sobolev space, if our design points, if you will, are nicely distributed and these noises or errors are IID sub Gaussian, then the smoothing spline estimator has a nice mean square error rate of convergence of n to the minus 4/5. This is the minimax rate in this function space. So we have a minimax optimal solution in the smoothing spline in this setting. Now there's a limitation though of linear estimators, and the limitation is that they really can't handle spatially varying smoothness. This isn't well captured by this Sobolev space. So here this blue function is a function that has slow variation in some parts of the unit interval, but then faster variation in this middle part here. And the red dots are data points that we're going to be using in our estimation. So we really get a trade-off. Either we have a large regularization parameter, and then we do a good job of sort of fitting in the smooth parts, but we sort of over smooth in this high frequency or fastly varying portion of the function and data. Or if we take a smaller value of lambda, then we can get these faster oscillations, but we also end up overfitting in the more slowly varying portion of the data. So we just can't adapt to the local smoothness of the function and data using linear methods like smoothing splines. So that's a limitation. So it turns out that moving to this BV2, this bounded variation space, sort of solves that problem. And so what we're going to do is we're just going to look at a similar variational problem, but instead of the integral of the square of the derivative, we're just going to look at the integral of the absolute value of the derivative. That gives us a semi-norm for this space BV2. The solution to this variational problem is not a cubic smoothing spline. It's something known as a locally adaptive regression spline. It's actually going to be a piecewise linear function that has this form. And this notation right here just means taking the positive part of the argument. That's what the sub plus means. We'll use that a lot in this talk. And this idea of solving this variational problem goes back to Fisher and Jerome, and then Mammon and Vandegeer in '97 really developed the statistical analysis of this type of approach. And it turns out in this case that the coefficients, the alphas in this locally adaptive regression spline can be obtained by solving an L1 sort of minimization that you see here. And Ryan Tibshirani has a very nice paper that explains all this, how L1 regularization actually solves this locally adaptive regression spline problem. And because it's L1 regularization instead of L2, the solutions are nonlinear in the data. So you can't write that as a linear estimator, but it has, again, enjoys a nice minimax optimality. If our optimal regression function F star that generates our data lives in this BV2 space, then the locally adaptive regression spline also achieves this rate of convergence of n to the minus 4/5, where again, n is the number of data points that we're using in this method. And so it gets the same rate as the smoothing spline, even though it's able to handle these problems in this much bigger space, BV2. Of course, it would get the same rate n to the minus 4/5 if we were in the Sobolev setting as well. So another approach that can sort of handle this BV2 case is wavelet thresholding methods. And so we can represent a function in terms of its wavelet series. I'm just showing the Dobeschi 4 wavelet there on the right. And the basic kind of the key idea of wavelet methods is that we can approximate many functions very well using a sort of nonlinear approximation in terms of wavelet terms. And so the notion is that we have let f sub m denote the wavelet series approximation using the m terms with the largest coefficients. And if we look at m term approximations of that form, then if we have a function in BV2, the m term approximation error decays like m to the minus 4. Okay, so it's a pretty good approximation rate. And if you just do a little bit of back of the envelope balancing approximation error and variance, you can end up concluding, and this can be proved formally, Donohoe and Johnston did amazing work on this back in the 90s, that the wavelet thresholding estimator, it's a nonlinear estimator, and that estimator also enjoys this n to the minus 4/5 rate. And one of the other sort of really important contributions in the work of Donohoe and Johnston is they showed that any linear estimator, including smoothing splines, can't achieve that rate. It can only get up to a rate of n to the minus 3/4 in this setting, in this bounded variation setting. And so there's a real gap between what you can do with linear methods and what you can do with nonlinear methods like wavelet thresholding and the locally adaptive regression. So here's what solutions look like in the same data fitting problem that we looked at before, our original function and the data points, the wavelet denoising result shown in blue here, and the locally adaptive regression spline shown in blue below. And you can see in both cases, they're sort of adapting to the local smoothness of the function. They're able to capture those quick variations in the middle, but also not overfit to the data in the smoother portions of the function. So they're adapting to local smoothness. And that's one of the big sort of capabilities that you get with these nonlinear methods, nonlinear estimators. All right, so where do neural networks fit into this story? So here I'm showing a single layer neural network. So we have our input. We take weighted combinations of that input. The weights feed into these neural network activation functions. And then we have a set of weights that are taking the outputs of those neurons, summing them up, and that gives us our overall function. So we could write that down like this. We have an activation function. We have this affine function, wjx minus bj for each neuron. That's kind of going in. I'm not showing those offsets or biases here in this picture just so it doesn't get cluttered, but those are important. Those are included. That's a tunable parameter too for each input neuron. And then we have our output weights, the V's. Now this nonlinearity that we were talking about, these are common activation functions over here, a step function, sort of on-off, a logistic or sigmoid type of function. And here's another very, very popular type of function called the rectified linear unit, or Relu. We're actually going to focus on that one because many, if not, well, I'd say most current neural network architectures use the rectified linear unit as its activation function for a whole host of practical reasons, but we'll also see that it has some really interesting theoretical consequences. So if we specialize to the so-called Relu neural network, again, I'm going to use this parentheses with sub plus just to know taking the max of the argument in 0. So that's also depicting what that nonlinearity looks like over here in these neurons. Here's our single layer Relu network, has this form. And you can kind of just recall that this is exactly the same form that we saw when we were looking at the locally adaptive regression spline. And this connection between locally adaptive regression splines, or L1 splines, was first kind of noted by this nice paper by Sarah Rees in 2019 and his co-authors, and then Rahul and I kind of expanded on that work a bit. And so one of the kind of amazing and surprising things is that the standard approach to training neural networks, and you might see this referred to as training with weight decay, what that really means is that they're minimizing using gradient descent, a sum of squared errors, or some other loss. It doesn't have to be squared error, but let's just stick with squared error for now, plus a ridge regularization of the neural network weights. So here are the neural network weights, the V's and the W's. We're just looking at the sum of squares of all the weights, so it's just a ridge regularization. And what's kind of surprising is that if you actually solve this optimization, it's exactly equivalent to the locally adaptive regression spline, even though it looks like we're using a kind of L2 type of regularization instead of an L1 regularization. And I just want to kind of explain where that comes from. That's one of the important things I think to take away from this first part. So the rectified linear unit is piecewise linear. And so what that means is that if I had a neuron with input and output weights V and W, I could just rescale V and rescale W with some positive number C. So I could make V larger by a factor of C and make W smaller by a factor of 1/C, for example. Okay, so that doesn't change the output of that neuron or the contribution of that neuron at all because of the piecewise linear nature of that rectified linear unit operation. And so what that means is that we can rewrite the standard optimization problem that I just showed you before with an extra set of parameters, these C's. Whatever value of C's, just positive numbers I take for each neuron, that will not affect the data fitting term because of this equivalence here. But I can I'll write the regularizer also involving this C extra parameterization. It just looks like this. And so now if you just said, well, what would be the minimum of this if I minimize with respect to C and hold the other things constant for a moment? So if I just look at the derivative of the regularizer with respect to C, because again, this is invariant to the choice of C, we see that the optimal value of Cj squared is just going to be the ratio of the absolute value of Wj to the absolute value of Vj. And what that means then, if you plug in that optimal choice of C there, you'll get exactly this equivalence, that V squared plus W squared is equal to twice the absolute value of the product of V and W. Okay, and this kind of connection between L2 and L1 regularization, when you have this bilinear parameterization in the neurons, was first noted in this paper by Granville 98, and also Neshaber and his collaborators kind of brought this up again and exploited this in some of their work in 2015. So what does it mean? It means that the standard way people train neural networks is actually equivalent to an L1 regularization of this form, where again, now the regularizer is the L1 norm of the product of the input and output weight of each neuron. And what that means is that the solutions to these training problems are sparse. And the number of active neurons, so the number of neurons with significant weights, no matter how many neurons we put into our neural network, the solutions will only end up with about N or fewer neurons with significant weights. Most of them will just dwindle down to 0. Okay, so it's kind of just like a lasso type of optimization. And this suggests new strategies for training neural networks based on things like soft thresholding. So I'm just going to kind of show you, I thought, well, what would it do? So I tried this out. What I'm looking at here is a neural network with training on 32 data points. So just a single layer Relu neural network, 32 data points. These are the blue dots that you see here. And I'm using 320 neurons. So I'm very over parameterized, 10 times more parameters than data points. And the neural network solutions are the blue and kind of magenta curves that you see here that do a job of fitting the data and kind of, but not overfitting it. And what happens is that both methods sort of eventually converge to solutions with 12 active neurons. So even though we started off with 320, there's this sparsification. So we get down to 12 in the end with a particular choice of the regularization parameter lambda. But what's interesting is if we, instead of following the usual gradient descent with weight decay, if we instead use gradient descent with soft thresholding, because we're aiming to solve that problem of L1 regularization, the equivalent one, we can see that we can converge to that sparse solution much, much faster. So this is the convergence in terms of sparsity. So this is sparsity versus number of training steps. You see the L1 regularizer really helps you find that sparse solution much quicker than traditional training methods. So I think there's clearly something that sort of a theory and method and algorithms from statistics might offer in terms of helping us develop better training algorithms for neural networks. Okay, so let me kind of just make a few observations here. All of these methods, smoothing splines, wavelets, neural networks, you can all view them as a sort of series type estimator. In the case of smoothing splines, we basically know that training a smoothing spline to fit some data is basically related to weighting or truncating the estimated Fourier series coefficients in a non-adaptive or linear manner. In other words, the weights in that weighted Fourier series don't depend on the specific y's and data points that you've observed. or that we truncate the Fourier series at a certain high frequency that has nothing to do with the specific data that we've collected. So those are linear methods. Wavelet methods use a dictionary not of Fourier basis functions, but wavelet basis functions. And the training, if you want to use the machine learning term there, is thresholding empirical wavelet coefficients to select a sparse set of the best wavelet functions to build up your estimator. So there's this sort of notion of best selection as opposed to just a linear weighting. And the neural networks are essentially doing something very similar to wavelets, except instead of using wavelet basis functions, the dictionary that we're using are these neurons, so these rectified linear units, where W and B are parameters of those functions. So this is a continuous dictionary. That makes it a little more tricky, but the training by gradient descent weight decay is equivalent to training with gradient descent soft thresholding. And that's also then allowing us to select a best set of neurons to estimate a function that we're trying to learn from data. And so the main message that I just want to kind of get across here is that standard neural network training methods are implicitly employing an L1 type of regularization. This leads to sparse and optimal solutions, even if you take a neural network model that has many more explicit parameters than data. The solutions are also adaptive to local smoothness because they're equivalent to these locally adaptive regression splines. So here's just kind of looking at all of the methods together. Our test function and data, wavelet denoising, neural network equivalent to locally adaptive regression spline, and then smoothing splines, where we're choosing either a larger or smaller regularization parameter, but we face this trade-off. We can't adapt to the variation in smoothness in different locations in this function. And we have this little table here of all the sort of mean squared errors, and you see that the minimax rate in this kind of setting for this sort of function is n to the minus 4/5. Wavelets and neural networks can handle that. They also get that rate in this classical Sobolev case, but linear methods like the smoothing spline can't achieve that minimax rate in this setting. Okay, so I want to kind of go a little bit more into where some of the theory comes from. And one kind of idea that connects smoothing splines to neural networks is this notion of a representer theorem. So this goes back to the famous work of Kimmeldorf and Wava. Again, they said that, or showed that the smoothing spline is the solution to this variational problem that we looked at before. Now, what Rahul and I have shown is that there's also an analogous neural network representer theorem where you look at, again, a variational problem, data fitting plus some semi-norm regularizer. In this case, the semi-norm regularizer, we're just going to generalize it a little bit to look at the k plus first derivative of the function. The solution to this variational problem, or a solution, I should say, because there could be multiple solutions, but there are solutions that are of the form of a single hidden layer Relu K neural network. And Relu K is just the same thing as the Relu, except raised to the kth power, where K has to do with the order of the derivative that you're taking up here. And so we have this very simple expression for the solution to this variational problem. And the number of neurons that you need in this kind of representation is less than or equal to the number of data points. In fact, you can find solutions that are slightly sparser than the number of data points, and that depends on the degree of the derivative that you take here. I just also want to point out that this notion of a representer theorem in this setting actually goes back to the work of Fisher and Jerome, and also appears in the work of Mammon and Vandegeer. And sort of some of the things that Rahul and I did were connect this to neural networks, and then also really kind of nail down the existence of solutions and the sparsity level of these solutions. So these Relu K neural networks are minimax optimal estimators for BVK spaces. And these are just the generalization of the BV2 to higher order derivatives. And so I borrowed this slide from Ryan Tibshirani. He used it in a talk he gave on some of these locally adaptive regression splines and so forth. But it's just, again, illustrating that the Sobolev class is a subset of these total variation or bounded variation classes. And wavelets, locally adaptive regression splines, a method called trend filtering, which Ryan has worked a lot on, and also these Relu neural networks are all achieving the minimax rate in these total variation classes, whereas linear methods can't achieve that same rate. They're just slower in that case, although they get the optimal rate when you restrict to the smaller Sobolev classes. So just to kind of bring us to the sort of end of the first part of the talk, I just want to be a little bit more careful about what we talk about in terms of these bounded variation spaces and go back to this notion of distributional derivatives and so forth. So the reason we need to think about that is if we look at the rectified linear unit, so I'm drawing a rectified linear unit right here, it turns on at a certain point and then is linear after that point. So that's what a rectified linear unit would look like. I can take the derivative of that. I have a weak derivative. It's just a step function. And if I take the derivative of that, then that's a distributional derivative because it's actually just going to give me a Dirac impulse at the location of that step. Okay. So kind of when we write this sort of integral of the absolute value of the second derivative, we're sort of a slight abuse of notation there. Technically, what we need to do is define this semi-norm in terms of measures. And so more precisely for any function in this BV2 space, there exists a sign measure nu. So we can decompose that into its positive and negative portion, such that if I take the second derivative operator and apply it to the function f, it produces that measure nu. And then we can define the BV2 semi-norm in terms of the total variation of d2 of f. And so we're looking at the second derivative of f, and the total variation norm or semi-norm of that is this nu, which is the result, the measure resulting from that differentiation operation. So we can write it out like that. Now, what's important, if that's like a little confusing or you're not super familiar with measure theory, it just means that it coincides with the idea that if f really was twice differentiable, then this is exactly what we were writing before. But technically, we need to really think about it in terms of measures because we're going to end up with generalized functions like Dirac impulses. So the neural network representer theorem kind of is using this bounded variation norm that I just introduced, and the solutions are single hidden layer neural networks. And just to kind of be clear about this, what happens, the solution has rectified linear units or neurons, but it also has this linear portion. And the linear portion is due to the fact that this is the portion that's wiped out by the taking two derivatives. So you need to have that sort of linear component also in the solution. And in neural network jargon, they actually use this sort of thing frequently. They call it a skip connection. Was there a question or something, Lori? I see you popped back up.
Yes, Rob. Yes, so there is a question by Shiwang, and he asks for neural network representer theorem. The input is only univariate. Can Xi be a vector of
so
multiple inputs in the theorem?
Yeah, we're going to totally get into the vector case in the second part. It involves a little bit more machinery. So I wanted to first connect the simple univariate case to hopefully somewhat familiar topics like wavelets and smoothing splines. And then part two, we're going to deal with that multivariate case very, very carefully and thoroughly. So great, good. I'm glad there's interest in that. We'll get to it.
Thanks for asking the question.
Yeah, thank you. So I'm just going to kind of sketch how this is proved. It uses some really nice classical theory. So first of all, this differential operator, if you look at its Green's functions are rectified linear units, and its null space are linear functions. So that's again why we need these skip connections or this linear portion in our solution. So for each function in BV2, we can express it in terms of this measure. So in particular, the second derivative of f is equal to that measure. And then the problem of minimizing total variation subject to linear constraints, the linear constraints are our data fitting constraints here, is the so-called measure recovery problem. This is a classic problem, goes back to the late 40s, and it's been known for a long time that solution is a sum of Dirac impulses. And so we kind of, or a solution is a sum of Dirac impulses. And then if we look at the pseudo inverse in our setting, so the pseudo inverse of D2 is just integrating twice. If you integrate twice a Dirac impulse, you'll exactly get a rectified linear unit. Integrate once, you get a step function, integrate again, you get this step or ramp function. So that's kind of where it comes from. It goes all the way back to this classic work on measure recovery. So I'm going to kind of wrap up this section now. So what basically all this is telling us is that this BV2, bounded variation space, is the function space of infinite width. That's what these are sometimes called, Relu neural networks. So infinite width is a term used when people express functions in terms of an integral of neurons against a measure nu. So that's an approach and term that comes from the machine learning area. They call that an infinite width neural network. And if you look at all the functions you can generate this way, that's exactly this BV2 space. So we have neurons, and effectively what this integration is doing is taking an L1 combination of neurons. And if you like, you could think of, if this measure nu has a sort of density, then you could just think of this total variation norm as sort of like the integral of the absolute value of that density P. So here the measure nu, I chose nu because it looks like V, because in fact, that's exactly the role played by nu. It's playing the same role as those output weights V in our finite width neural network, our practical neural network. And so the idea to keep in mind is that fitting a data set with an infinite dimensional neural network function is approximately the same as minimizing the L1 norm of the output weights for a wide but finite width practical neural network. So that's how you would do it practically. And that's the end of the first part. In the second part, we're going to go exactly to the question that somebody was asking about: how do we generalize this when X is vector valued, the input to the neural network? And so that's what we'll talk about next. And I'm happy to take any other questions now.
So just letting everyone know that we are now opening the floor for discussion and questions. And you can unmute yourself, or let's see. There is a raised hand here, not mine.
So Flori, there are a few questions here. If you want, I can relay them to Rob. Is that okay?
Yes, please, if you can, because yeah, right. Yes.
Okay. So the first question says, will the slides be available after the talk?
I'm totally happy to make them
Rob,
available.
So I think, Rob, there is this place called the files. If you upload your talk on the files, maybe all the participants can get access to it. Okay.
Just
so
made
then
a note of it, definitely.
Michael Stein has a question which says that smoothing splines have a Bayesian interpretation as a conditional expectation under a Gaussian process. Is there a Bayesian interpretation to this problem of BV2?
Yeah, I suppose so. If we just think about the usual Bayesian interpretation of lasso, it'd be like taking a Laplacian prior on the coefficients, right? That would lead naturally to an L1 type of regularization. So I suppose that would be the most easily relatable way to think about it in a Bayesian way. I don't know if that helps with Michael's good question, but that's the way I would first start thinking about it. It's just the same way we do with, say, lasso methods and so forth.
And I have a comment here from Terry Sarno. It's more of a footnote, and it seems related to Freeman's Mars algorithm. I'm not sure when it was sent. So
yeah, I saw that too. That's yeah. A great observation, and if I'm pretty sure that's multivariate adaptive regression splines or something. Yeah. So yeah, I think it's totally related to that. And in fact, if you, I think in the next part of the talk, I'll mention various work. I'm not going to mention Mars specifically, but one of the papers I'll refer to by Francis Bach from 2017 makes a lot of connections to various methods, including Freeman's Mars stuff. So yes, totally related. Great observation. Thanks, Terry.
And there are some raised hands. Maybe Bodhi, you can, you have, I lost the name of the raised hand.
So there are a few other questions. Maybe I can finish that and go to the raised hands after that. So Aditya Guntuboyne has a question: is weight decay the standard way of parameter estimation in neural networks?
Yeah, so if there is any explicit regularization in neural network training, I would say that this idea of weight decay, which is equivalent to just adding a ridge regularization term to the overall objective, is the most common. So this weight decay would be the most common form of explicit regularization. Now, it is also true, though, that in many cases, people are not regularizing neural networks, at least not explicitly. They may be doing early stopping or other sorts of things. And so, yeah, I don't want to give the impression that everybody's always using weight decay, but it is, if anybody's doing explicit regularization, that's by far, in a way, the most common. It's built into all the packages. It's just an option, weight decay.
So Rob, there are a couple of other questions. So
Sure.
Wenzhou asks, is it possible to generalize the neural network representative theorem to the multi-layer Relu network?
Yep, that's going to be in part 2. We're going to go to multivariate and deep multi-layer. So hold on.
Okay. There's another question which says, why does one have to pass in the L1 and L2 norms separately when modeling the networks if the training is neural network is inherently with L1 norm?
So again, what's true is that if you train with a ridge regularization term, then that's equivalent to L1. So as I was kind of showing in, can I go backwards? How do I go back? Where am I here? Yeah, let me just go back to this picture here. Yeah, so here, I could just use the standard training. When I say ridge regularizer, I just meant literally I was in PyTorch, which is a popular software package for doing this, and I had weight decay on with a certain weight decay parameter, which corresponds to lambda in the ridge regularization. And so that's what I'm showing here. That's the blue decay. This is sparsity versus number of epochs. So you definitely converge to a similar sparse solution. They're not exactly the same because these are non-convex optimizations, so they might fall eventually into slightly different but comparable solutions. That's what you see here. But if we actually explicitly use the L1 regularization, we also converge to an equally good solution, roughly the same sparsity, but much, much faster. So I hope that kind of answers the question. It's a good question.
Thanks. So Flori, do you have more questions? And I don't really see any raised hands.
So I did. That's so perhaps the folks who raise their hands can send us a quick message via chat. There were a couple of people who raised their hands, but that just flashed over my screen, so I don't have a record of that.
I do see one question in the chat from Fabian.
Right.
I'll just take that.
Yes.
Yes. Are the norms of the parameters in the representative theorem related to the BV2 norm? Yeah. So it's exactly that. It's exactly that norm here that we're using, and that norm in the case of a neural network model will just be this sum of the absolute values of the products of those input and output weights. So we can actually write this norm down explicitly for a neural network model. And we'll see that again in part 2. So hopefully that'll become super clear when we go to the multivariate and more general settings too. So great for asking that. And we'll see it again in a minute.
So Rob, there is another question which says, how do these findings apply to convolutional neural networks?
Yeah, so I'm not going to talk at all about convolutional neural networks. Convolutional neural networks are, of course, super popular and the most widely used for things like image processing, image computer vision types of applications, like the classification ones we looked at. Yeah, so I'm not going to really, I think that's a great avenue for future work. This work really just focuses on sort of what you might think of as the most classic, fully connected, feed-forward neural network type of architectures. If that person's interested, they can ping me afterwards. I can point them to some work that tries to make connections between standard feed-forward models and convolutional neural network models. And there's some evidence that you can even just learn those convolutional structures from data as well. You don't really need to necessarily bake that into the process, but we can take that offline. Is there anything else?
So Rob, if I may ask a question. So so you basically highlighted this adapting to local smoothness of this classes of functions and that the kernels cannot do it. Now, I would imagine, is there a theoretical way to quantify this through local rates of convergence? Because it seems you're trying to depict something to pictures, but the measures you are using are still global measures. And I'm trying to understand if you can do something local there.
Yeah, that's a great idea. I suppose you could. I mean, you have to have some sort of assumptions on what you mean by local and so forth, and how local, how the smoothness it was at least locally behaving. And for example, if you said, well, I can have a local Lipschitz constant that's valid over a certain interval, I think you could totally work that stuff out through this approach, because what's going on is you're able to choose the weights, which are the slopes essentially of these piecewise linear portions that you're learning with the neural network, and then you're also able to shift them around. That's that bias or offset B, and so you can kind of very locally do everything you want. And localization, in the sense that I'm using the term right here, is something that's super easy to do in one dimension, because I can just take a unit and turn it on, and then a complementary unit to turn it off. So it's very easy to build localized functions in one dimension. It's much harder, and that's one of the challenges in the multivariate setting that we'll see, that that's one of the reasons we go deep. And so I'll talk about depth and localization towards the end of the talk.
Thanks, Rob. So I don't think there are any more questions.
Well, so I want to make sure that the folks who raise their hands don't feel ignored. The hands did not stay raised. So you've just flashed on our screens and then disappeared. So if you'd like to ask a question, please don't be shy and send us a chat message.
Yeah.
And then we'll know what the question was.
I'm happy to stick around as long as people like. And if somehow we get cut off and people want to follow up with me, I'm happy to do that too. So I can always do that. But maybe now I'll move on to the second part. How about?
Yeah, I think that's a good idea. And please do not forget your questions. So yes. Perhaps you already answered them. So yes.
Yeah. Good. Okay. So now we're going to talk about multivariate and deep. And first of all, I'm just going to look at multivariate, and then we'll go to the multi-layer or deep sort of setup after we get this sort of established, because this kind of gets at a lot of the core ideas and challenges just looking at the multivariate case. So just to begin with, one of the things that you'll hear a lot about if you start looking at neural networks is this notion of universal approximation. And roughly speaking, a universal approximation theorem says that if the activation function that we're using in our neural network is not a polynomial, then neural networks are dense in the space of continuous functions on some, say, compact set K of RD. And so this idea of universal approximation, of course, is sort of like a Weierstrass type theorem, but in the context of neural networks, it goes back to Sabenko, and then Lesho and his collaborators in '93 really did some nice work kind of with this idea of all we need is a non-polynomial activation function. So in particular, the rectified linear unit that we've been looking at is not a polynomial. It's piecewise linear. That's definitely not a polynomial function. So that's nice, but it doesn't really tell us, how well a neural network will work for estimating a function from data. So it just tells us that neural networks exist that can represent functions well. It doesn't tell us how many neurons or how well they are, how good they are at approximating, and it certainly doesn't tell us anything about what happens when we try to train them to fit data. So I want to kind of come back to this way of thinking about a neural network or an infinite width neural network as an integral of the neuron function with respect to some measure nu. So that's where we left off last time. We're going to write the same thing that we had before, except now the input X, and of course, then the weights are going to be multidimensional vectors in RD. And so what's known, and this is sort of one of the kind of amazing features of neural networks and neural network function spaces, is that if we're on a bounded domain, a function that has this kind of representation can be approximated in squared L2 norm to accuracy 1 over m using just m neurons. So I only need m terms to get a 1 over m accuracy and approximation. And this goes back to this classic observation of Maury and Pizier. And then Andrew Barron in 1993 is the person who really brought this into the context of neural networks. So it's kind of shocking because it's sort of saying, doesn't matter what dimension the input is, D could be anything here, it could be 1, it could be 100, no matter what, if the function has this form where it can be expressed in terms of an integral with respect to a bounded measure nu, then we have this dimension-free approximation rate. And so that kind of shocked people. People said Andrew Barron broke the curse of dimensionality. And in some sense, there is a big contrast here, because if we look at classical multivariate function spaces, Holder spaces, Sobolev spaces, et cetera, they're going to require m to the d terms to achieve such an error. So m to the dimension. So kind of this exponential growth in terms of dimension. So what's going on? How is this possible? I want to just kind of talk about it, kind of explain my way of thinking about it a little bit. So infinite width neural networks, they have this form where this measure nu has some bounded total variation, say some bound b. What this means is that we can approximate a neural network, an infinite width neural network function of that form with a finite width neural network. And that finite width neural network, the analog of this total variation here is just going to be the L1 norm of these output weights. And we're just going to normalize the so-called input weights, the W's, to have unit norms. So we'll absorb all the scaling into the V's, and then we just can write that as the L1 norm of the output weights. So this is an L1 bounded combination of neurons, and each of those neurons has a preferred direction determined by the weights that are going into the input of that neuron. And so what this does is this allows for functions that can vary a little in many, many directions in RD, or they could vary a lot just in, say, one direction, okay? And so because of this, Donahoe, in one of his kind of papers, I guess it was, a little bit longer, he kind of did a review on high dimensionality, and he called these mixed variation spaces, which I think is a perfect term for them. And I want to kind of show you what this looks like. So what is a mixed variation space? It's a space in which you could have functions that maybe have weak variation in many directions. That's what I'm showing here on the left, or strong variation, but only in one direction in the function space. So here I'm only looking at two-dimensional functions, but you could imagine this story in higher dimensions. And so the point here is that both of these functions have the same total variation, but classical norms like Sobolev space norms in multiple dimensions are smaller for this type of function than they are for this type of function. And so what this means is that neural networks sort of favor functions with variation in limited directions. Okay, so that's something to keep in mind. So it's not like magic is happening. It's just that these neural network spaces, if you look at the space of neural network functions with some bounded total variation measure B, bound on that measure that I had up before, that's giving you a bunch of functions which can either vary a lot in all directions, but very weakly, or they can have a lot of variation, but only in a small subset of directions. And that's what's different between those spaces and classical multivariate function spaces. So this kind of leads to this interesting question. Are we doing, with neural networks, are we doing interpolation or extrapolation? And Jan LeCun, who many of you probably know, I hope this is okay. I took his tweet from a couple of weeks ago, or a few weeks ago. He was talking about somebody who was explaining neural networks through this idea of universal approximation theorem and data interpolation. And he was basically saying, no, it's totally not interpolation. And I think his last sentence there is the key one. In high dimension, there is no such thing as interpolation. In high dimension, everything is extrapolation. And I want you to think about like those image processing or image classification types of tasks. The input dimension is, say, a 256 squared pixel image, right? So that's a very high dimensional input dimension. And we might be training on a few thousand or maybe a million such images, but still that's a small number of data points in very high dimension. And so a lot of what's going on with neural networks is probably more extrapolation than interpolation. And then that's just like a funny little cartoon about extrapolation. So we have to be careful is the point. Neural networks are doing something, but what are they doing? So I want to show you what they're doing. So again, I can't show you the picture in super high dimensions, so I'm going to try to illustrate it in 2 dimensions. So suppose I had this function. So the background image here is a 2-dimensional function with strong variation just in one direction. And let's just suppose that my data points where I measure that function are only the red dots that I show you here. So they're only measuring kind of in a localized region of the 2-dimensional space. Now, what would happen if we use this classical kind of linear method, a kernel method, for example? So a linear estimator kernel method would probably end up giving you an estimate that looks something like this. So it's basically picking up these 2 bright areas and this dark area, and it's saying, well, I have no data out here, so my extrapolation is 0 away from the data. Seems like a very reasonable thing, and I'm not saying it's not reasonable. It may be very reasonable. But neural networks do something totally different. Here's what, if you train a single layer rectified linear unit neural network to fit those data, this is the solution that you get. So it just takes the pattern that it sees along in the support of the data and just extrapolates that in all directions. Okay, so that's kind of a very different type of extrapolation that we're seeing with neural networks compared to classical multivariate estimation techniques. So that's something I just want people to keep in mind. I hope that makes some sense. All right, so let's just talk about approximation and estimation with rectified linear units in multiple dimensions. So again, the infinite width neural network, I can write it this way against some measure. We know we can approximate that with a finite width M neuron neural network, satisfying a squared L2 approximation rate of M to the minus 1 plus 3 over D. And so this exponent here is kind of interesting for high dimensions. Basically, it's just M to the minus 1, but in low dimensions, it's a bit better than M to the minus 1. And this is coming out of that paper I mentioned from Francis Bach, and also then Siegel and Zhu have a really nice paper that's just appeared on Archive recently that extends this to a lot of other interesting cases. And it's a really nice paper that both of these I recommend highly. And I should mention at the end of these slides, I'm going to have a list of all the papers that I've mentioned, so it's easy to find them if you want to go back and look. So at any rate, what that means is if we estimate a function in this class, and by this class, I mean the functions we can generate by so-called infinite width neural networks, then if I have n nicely distributed samples on some compact set omega, then I essentially, again, the back of the envelope calculation, you can make this more formal, but the back of the envelope calculation is saying that, well, your approximation rate is at least like M to the minus 1, and then your variance is like M over the number of samples. And if you balance those terms, you get this N to the minus 1/2 rate. And by this tilde, I'm just going to be hiding logarithmic factors and so forth. So it's basically like 1 over the square root of n is the rate. So that doesn't have anything to do with the dimension of x. And that's because of the special restricted class of functions that we're looking at here. If we were to specialize this to d equals 1, then you notice that I get an exponent of 4 up here. That's exactly what we saw with the wavelet methods before, and we get this n to the minus 4/5 rate. So you can do better in low dimensions, and that just pops right out of this work by Bach and Siegel and Zhu. So that sounds great, but isn't this a bit circular? So what is this really saying? It says that finite width neural networks are very good at estimating and approximating functions that are generated as infinite width neural networks. So it's sort of like, yeah, neural networks are good for neural networks. And that's not totally satisfying. What we'd like to know is what exactly are these function spaces? What kinds of functions am I generating? I have some sort of intuitive notion. I showed you that with these pictures of mixed variation spaces, but can we characterize them more precisely? So that's what I want to talk about next. So just to kind of set the stage for that, people have tried to develop what you might call neural spaces. So Andrew Barron's work in '93 was maybe one of the first attempts at this. And he had this interesting space that now people sometimes call Barron space, which is you're looking at functions whose Fourier transforms, capital F, satisfy a sort of L1 Fourier condition that looks like this. And so it turns out that one of the big sort of things out of Andrew's paper was that functions that satisfy this condition also have these dimension-free approximation rates via L1 combinations of sinusoids, sigmoids, or Relu neurons. Another really kind of important piece of work, I think, is in Immanuel Kanda's PhD dissertation, where he introduced the idea of ridgelets, which are sort of a nearly orthogonal neuron-like system. Those neurons are called ridgelets, and these allow for stable and computationally tractable neural networks, at least when the dimension isn't too large. And he also introduced these ridgelet spaces, which are, roughly speaking, again, I might be mischaracterizing a little bit, but roughly speaking, it's like taking the wavelet Bezoff space idea, but looking at it in terms of these localized ridge functions, which he called ridgelets. And one of the key ideas in that work of ridgelets was working in the Radon Transform domain. And we're going to see that that's super important also to understanding these infinite width Relu neural networks and then extensions to deep neural networks. So what's the key idea? How do we get there? The key idea is sparsifying transforms. So the idea is that we're going to take an atom, or you can think of this as a basis element, and we want to find a linear operator L such that when I apply L to my atom or basis element, I get a Dirac delta. So kind of this is super familiar. If my atoms are sinusoids, then I take the Fourier transform, I get a Dirac. If I have a wavelet, or a little localized wave, if I take the wavelet transform, then I get a Dirac impulse. And so what we want to do is, in the case of a rectified linear unit, what is that linear transformation, or linear operator rather, that produces a Dirac impulse? Well, there are two parameters for the Relu, the sort of offset, or the place where it turns on, its activation point, and the slope here of that linear portion. And if I use the second derivative operator, I exactly get a delta function. It's going to be a delta with a weight proportional to the magnitude of this slope, and then it's going to be located at a location related to the B and normalized by that weight. I think there should be maybe the absolute value of W here. So that was we saw that before. That's exactly what we were looking at when we were looking at the univariate Relu networks and the locally adaptive regression spline. We saw the second derivative operator coming up, and it's coming up because it's the natural sparsifying operator for Relu functions. That's this whole Green's function business that we talked about before. So how do we do this in multiple dimensions? This is sort of like the big step and the key insight. So I want to make sure everybody's clear on it. So what does a multi-dimensional rectified linear unit look like? I'm going to show you what it looks like in 2 dimensions. So here's that univariate Relu function, but if I apply that to a 2-dimensional affine function like I have here, what I get is sort of this 2-dimensional sort of ramp function that I'm picturing on the right. And so these are functions of this form are called ridge functions. That's where the term ridgelet and so forth came from too. And they're parameterized by essentially their orientation and their offset, or the bias of a neuron if we're in neural network language. And so if we look top down at this function, it would look something like this. The orientation basically tells me like in which direction is that ridge function oriented, and then the offset is just moving it around in the plane. So those are the parameters of these multi-dimensional rectified linear unit neurons. So why the Radon transform? It's like the go-to transform if you want to analyze multi-dimensional functions at different angles and offsets. So here I'm kind of just depicting a multi-dimensional function, its projection into along one direction, and then the profile is a function of the offset B in the Radon domain. And I can look at it from different angles and get different projections. So this is the idea that's probably familiar to people from computed tomography and things like that. So we're going to use that idea here. So this is how we use it to understand what's going on with a multidimensional Relu neuron. This is an idea that was developed in this really nice paper by Greg Anji and his collaborators in 2020. And here's how it goes. So we have this Relu function. What we're going to do is then we're going to take the second derivative, which is just the Laplacian in 2 dimensions. Okay, and what's going to happen is that's going to annihilate the linear portion altogether, and we're going to be left with just what you might think of as like a Dirac line, right along this activation threshold of that neuron. Then if we apply the Radon transform to a line, we essentially get a point. And so it takes the Radon transform of this derivative of the Relu gives us a Dirac impulse, and that impulse is located exactly at the orientation and offset in the Radon domain of that neuron. So this differentiation followed by Radon transform exactly sort of peels off what are the parameters of that neuron. And that's a really cool insight that they had. So what does it look like? So we have, again, our multidimensional Relu. We apply this operator Laplacian plus a Radon transform. This is just a filtering operation associated with the Radon transform. And what that gives us is a Dirac impulse. Its height is going to be the 2 norm of the weight vector of that neuron. And then it's going to be located in the Radon domain at the location of that orientation and offset. And so this is just to kind of illustrate what this is doing for us. If I had a rectified linear unit function f that's built from 7 neurons, this is what the function looks like. If I look at it from the top down, I get that coloration you see there, here. And then I'm going to take the Laplacian of that. And what that results in are just these 7 lines. One line associated with the activation threshold of each neuron. And then if I took the Radon transform of those lines, I get Dirac impulses in the Radon domain that tell me exactly the orientation and offset of each neuron in that system. Okay. So here is what we're going to do. We're going to introduce a neural space. It's going to be a Banach space, and this is what it is. I'll call it, this is a notation. We're going to call it Radon BV2 because we're using the Radon transform to analyze this multidimensional setup. We're going to do roughly what we were talking about before, where we take the second derivative, but we also are going to then transform into the Radon domain and then look at this total variation measure in the Radon domain, because that's where we expect to see these deltas, these Dirac delta or impulses, if we really were analyzing a neural network function. So basically what you can think of this as doing is measuring the sparsity of the second derivatives of f in the Radon domain. So, and this is getting back to a question that came up before. How is this semi-norm relate to the weights of a neural network, for example? If this function f doesn't have to be a neural network, but if it is, what is this semi-norm? What is this total variation? Well, you can actually explicitly write it out. You just get this form right here. So if I have a function that is a finite width neural network, you just get something that's usually called a path norm, just the absolute value of the output weights times the 2 norm, not squared, just 2 norm itself of the input weights. And so that's, again, in the one-dimensional case, that would just reduce, or the univariate case, just to the product of v times w, the absolute value of that. So we recover that kind of case in the univariate case, but this generalizes in this way to multiple dimensions. So we have a really nice way of writing that. So here is the multivariate neural network representer theorem. We can actually have any loss function. It doesn't have to be a squared error, but any lower semi-continuous loss function. So you could be doing logistic regression or whatever you want here. But if you like, you just think of this as squared error again. Then we're going to regularize our data fitting with this RBV2 norm. So the norm I just defined on the previous slide. And if I solve this variational problem, it admits a solution that has exactly the form of a single layer Relu neural network. And you also see again this linear portion, which is in the null space of that differentiation operator. The number of neurons that we need, k, can be less than the number of data points, in fact. And so we have a kind of sparse solution. So no matter how many neurons you start off with in your neural network, if you solve this variational problem, you'll get a neural network that has, at most, the number of neurons equal to the number of data points. So this is just one way to kind of maybe visualize a little bit why they called it a skip connection. It's sort of like you have your input going into your nonlinear neurons, but then you actually just replicate the input again. That's why it's called skip. And that's the linear portion that also is part of your overall output of your function. And I'm not going to go back over how you prove this, but it basically follows the same sort of reasoning that we had before. It's this classic measure recovery problem. Okay, So what can we say about this neural space? It turns out, and this is something you can basically see by looking at the paper I mentioned by Siegel and Zhu, but what we have is the barren space, which Andrew introduced back in '93, can be really thought of as being generated by linear L1 combinations of decaying sinusoids. So that was sort of what was going on there. If you instead take L1 combinations of rectified linear units, you can cover everything you have in barren space and more. And so this RBV2 space actually includes that barren space. In some sense, it's a sort of completion of that, the full description of that if you use rectified linear units. So coming back to this question of regularization, how people train neural networks, again, what they normally be doing is applying gradient descent to minimize an objective that looks like this. So this is your neural network and the loss on your training data. This is just standard ridge regularization applied to the input and output weights. That's what you would be doing if you use this so-called weight decay. And because we have this piecewise linearity of the Relu neurons, for the same reasons that we talked about before, it's exactly equivalent to minimize, or the solutions would be equivalent if you just minimize sum of losses, but instead use this sort of path norm regularization, which is exactly the RBV2 norm of the neural network. And so these two optimizations have the same solutions. And so we can see that sparsity and the reason for it by just looking at it in this way. So that covers the multivariate case. Now I want to kind of move to multiple layers, it's called deep neural networks. And to do that, I first want to extend things to multidimensional outputs. And we're going to do something really simple here. We're just going to say, oh, instead of having just one scalar valued output, we're going to have multiple outputs, and each output is going to be its own function, say F1 through FD out, if there are D out dimensions here. And we're just going to have each of those component functions live in its own RBV2. And so what that means is we're just going to define a space RBV2 mapping from RD in to RD out, so input dimension to output dimension, which is just a product space, D out times. So that's a really simple way to do this. And then you can define a norm on this product space, which is just the sum of these norms. This will give you a way of expressing a norm here. So these are the RBV norms of each individual component function. And then this L1 norm is the L1 norm of all of the linear portions, the things that are annihilated by the differentiation operator that you still need to have in your solutions, those just linear functions, the so-called skip connections. So you also regularize those to get a valid norm here. Now, to go deep, we're just going to take the multivariate output space, and we can now use that to define a compositional function space. So we're going to define RVV2 deep just to be compositions of those functions that we just defined before. And what we specify here in these deep spaces are the dimensions of each layer. So D sub L is the dimension of each layer. I'll show a picture in a second just to illustrate this. But that is how we're going to define a compositional function space. And it turns out that if you do that and you define a norm or a sort of a norm, this is exactly a norm, but it's just the sum of the norms of each layer. If you use that as your regularizer here in this variational problem, the solution is exactly a multi-layer rectified linear unit neural network. So this tells us that, in fact, what these multi-layer rectified linear unit neural networks are doing is they're representing functions in this deep compositional space built up from this RBV idea. So here's an example with 3 layers. So you say, well, I have an input dimension of 4. I want my first layer to be dimension 8, second layer dimension 8, and then the output, let's say, was 2-dimensional. What we don't want to do is limit in any way how complicated our function can be at each layer. So we could use as many neurons as we like. So we kind of get this kind of special structure as a result of that representation theorem. It says you can have an arbitrary number of Relu neurons in each layer, but we've said that we want each function to have a certain output dimension. So we've specified that. And so this is what the architecture actually ends up looking like in those solutions. There are also the linear portions that I'm not showing, the so-called skip connections. So what is this kind of norm that I defined? You can write it in terms of path norms of all the neurons in your neural network. So it kind of has a form similar to what we saw before, with the path norm of each rectified linear unit, the orange nodes here, and then the L1 norms of the linear components of the solution. And it turns out that this is almost equivalent to ridge regularization, but a little different. So you can show that this is equivalent to a norm that looks like the one I'm showing you here. And here I have a squared 2 norm, but here I have a squared 1 norm, and I also have the 1 norms here. So there's a little bit of a difference here. This suggests maybe there would be different kinds of regularizers might be actually beneficial in training deep neural networks. So maybe modifications from the standard weight decay and ridge regularization. So let me just show you experimentally what happens if you train a neural network like this. So we chose a neural network that has 4-dimensional input, a 16-dimensional internal layer, and a 1-dimensional output. And we're going to allow in our model 1,296 rectified linear units in each layer. And in the experiment, we're going to have, I think, 81 data points that we're sort of fitting to. So we're in this very over-parameterized setting. So this is one way to visualize what happens when you train in a neural network in various ways. So this internal weight matrix is the product of the outputs of this layer and the input to the next layer. So it has this factorized form V times W. So that's the form that naturally comes out of this representation theorem. And if we train the neural network and regularize using this RBV2 deep regularization scheme that I just showed you, this is a kind of heat map of the magnitude of this overall 1296 by 1296 weight matrix between the two rectified linear unit layers. And so you can see it's mostly 0. There's sort of this sparse and low rank structure just because of this factorization. So if I actually show you the factorized matrices, the V and W corresponding to these weights, you can see that there's essentially just 2 active neurons in that layer when we trained it. If instead we use standard weight decay, so that kind of puts everything as squared 2 norms instead of some of the L1 norms that we saw in the previous slide, you get a very similar solution, except there's a lot of redundancy in the weights. So it's less sparse, and in fact, it's still very low rank because we're forcing it to have the same architectural structure. And so these are just kind of replicated neurons that are not sort of sparsified in the way they are if you use this RVV deep regularization. And then just another thing we do is we could say, well, forget about the factorization that the representation theorem suggests, just use a fully connected set of weights. If you do that and just use standard weight decay, you get something qualitatively quite similar. It's fairly low rank. It's quite sparse, mostly 0. So weight decay definitely still is doing something in the way of sparsity, just maybe not as strict as we get if we use the factorized forms from the representation theorem and the sparser regularizers. And then going back to this idea, what if we just train with no weight decay, no explicit regularization? Well, you just get a very, very dense network, so no sparsity at all. And that's what we would expect. So all this kind of comes out if you actually run these experiments using the standard packages. So kind of to wrap up, I want to get to one point that we haven't talked about, and that is the benefit of depth. Why have a deep neural network? Why not just use a very wide single layer neural network? Okay, and so the reason is that because a single layer of a neural network is essentially a superposition of ridge functions, their ridge functions are non-local. And so it's very hard to represent and then therefore very hard to estimate from data functions that are localized in space. So here I'm showing a localized function, a pyramid function. It turns out that this function isn't even in a single layer neural network space. It's not in RBV2. but it is in the deep RBV spaces. So what that means is that if I were to collect measurements of this function, say the red dots, if I use a shallow or single layer neural network, both of them will be able to perfectly fit these data, right? Because of course they're non-parametric and I only have n training points, so I could fit them with a shallow or deep neural network. But what's going to happen is that we're going to get, the shallow neural networks are going to have very large weights because it's hard to kind of fit a localized function like this with ridge functions. And that's going to lead to very poor sort of generalization stability to new examples. And so deep neural networks really can give you this capability of localizing. So I want to just show you a picture of how that could be. So with a very simple single layer, I can take a combination of 4 rectified linear unit functions and create these sort of like ridge-like functions that you see here, where they're just sort of, they kind of come on, they go up, and then they drop back down. But these would extend infinitely long in the sort of other direction, but they'd be localized in this direction. I could alternatively localize in this direction. So I can do that again with just a combination of 4 Relu neurons. So I can build functions like this with 1 layer, and then I can pass those functions as the input to another rectified linear unit, which will just only allow things to pass that are, say, above a certain bias or threshold. And if I do that, I exactly get a very nice and localized function that looks like this. So with 2 layers here, I'm already able to start constructing very localized functions, things that would be extremely difficult to represent with just 1 layer. So this idea of spatial localization is something that I think is important in these deep spaces, but something also that maybe is sort of only understood a little bit at this kind of level now. There's a lot of people working on it, but this I think is one of the important features of depth in neural networks. So let me wrap up by just trying to kind of tell you what I think are the takeaway messages. So deep rectified linear units are the optimal solutions to data fitting in a particular type of function space, this RBV deep space. So we know exactly, it's kind of incredible. You can say neural networks are the optimal solutions to certain problems in certain function spaces. So that's kind of cool and important, I think. These spaces capture spatially and directionally varying smoothness. So we can not just, that directionally varying aspect is this mixed variation idea again. Depth allows for spatial localization, and these new mixed variation spaces suggest new statistical methods and new neural network training algorithms. And then I'll just also mention that the theory that we've developed here provides a lot of insight into some important properties that people have observed experimentally. Specifically, there's a lot of interest these days in sparse neural networks. There's a very active area of trying to understand sparsity in neural networks. So this sheds a lot of light on that. It also explains why we can use very, very over-parameterized neural networks and still have nice generalization capabilities. Skip connections, which are something that sort of was experimentally discovered, also called residual connections, to be super important in practice. These arise naturally as a requirement of the solutions to the variational problems we were looking at. And then we also saw how the variational problem in this deep context led to these low-rank structured weight matrices between the nonlinear layers. And there's been a lot of work recently also on introducing these low-rank structures to improve not only computational efficiency, but also statistical performance and generalization in neural networks. So this sheds some light on why that might be. And I think that's it. Those are the references. I'm not going to show you that. I'll just leave it on this slide. And really thank everybody for listening, and happy to take more questions. Thanks.
So we can imagine a big round of applause around, around the room.
If we were live, I would be trying to talk everybody into going out for a beer at this point, but
right, we have your
that for another meeting.
I think before we do that, we'll probably want to take some questions.
Yeah, I see Fabian had one in
yes.
the chat. Maybe I'll just read that one to begin with. So he says, do you have an idea about what would be the benefit of more than 2 layers? It seems like localization is possible with 2 layers. So people have thought about this, and I'm not going to try to quote the results off the top of my head, but Boris Hannon at Princeton University is somebody who's done some work on this from the approximation perspective, and he has some results that explain, exactly how much depth maybe you might need to get nice sort of approximation properties. And if I kind of remember, it's something kind of like logarithmic in the number of data points or something like that. But Boris Hannon, Hanin, is the place I would direct Fabian and anybody else if they want to learn more about the benefit of more than 2 layers, at least from the approximation point of view, which probably translates into some statistical benefits too, but it's all kind of very much new work that's coming out just in the last year or so. That's a good question. Other questions? I know that was a long thing. I thank everybody for hanging on.
So, Bodhi, do you have any questions on your screen?
Yes, I do. So there's a question that says, can you elaborate this connection? Okay, so just hold on. I think to a tree-based model or a DL tree.
Aha. So, a tree-based model, or I guess a deep learning tree. I'm not 100% sure I know how to answer the question, but I would say that when I think of trees, I think of some sort of partitioning, some sort of recursive type of partitioning of input space. And I can see, there could be possible connections between the type of functions and spaces you might be able to generate that way versus with this neural network construction. But the fact of neural networks being built up of ridge functions, right, and then compositions of ridge functions is kind of, to me, it seems fundamentally different than more conventional recursive partitioning tree-like structures. And that may be for better or for worse. I'm not sure. This coupling of the parameters across all the layers. Of course, I can localize a function using multiple layers, but it's kind of a complicated way to represent a localized function. I'd be much happier to just kind of do some sort of partitioning. So yeah, I'm kind of rambling a little bit. I don't have a great answer. I think there could be interesting ways to think about these neural spaces and maybe other ways to generate mixed variation spaces based on trees or other types of partitioning strategies. So hopefully that may be an interesting area of future work. And yes, I will figure out how to post the slides, and Bodhi and Flori can help me if I can't find my place, but I'll definitely post them. Happy to do that. And if you have any trouble finding them, just shoot me an email. I'll put my, well, I can't put my email in the chat, I guess, but it's easy to find me. So let's see. I don't know, so, there was another thing that came Rob, up. Yeah, go ahead, Bodhi.
There's another question. Is there any connection between the mixed function variation space and using the spike and slab prior?
Sorry, could you say that last part again?
Between the mixed variation function space and using the spike and slab prior.
Spike and slab prior. Okay. That's a great question. I don't know. I'd have to think more about it. I don't have a great, I'm familiar with the spike and slab type model idea. That's a great question. I'm gonna make a note of it, but yeah, off the top of my head, I'm not sure exactly how to answer it. Great question though. I'll think about it. And if that person wants to follow up, I'd be happy to. I see a question here in my chat that I can see, wondering about neural networks with activation functions other than Relu. Yeah, what can be said? So that's a great question. So in the beginning, the univariate case, I talked about these Relu K functions, which are essentially truncated power functions. K = 1 is the Relu, K = 2 would be truncated quadratic, and so forth. All of these basically end up giving you these classical L1 splines of varying degrees in the univariate setting. And you can do all that in the multivariate setting as well. You can use truncated powers of higher orders. Now, if you try to do something with other types of activation functions, say sigmoid or logistic or something else, things aren't quite so clean because one of the key things we're using here is the sort of homogeneity of these activation functions. That was what we were using to make this connection between the ridge regularization and the L1 type of regularization. So we have thought a little bit about what could you say about other activation functions, and there are some sort of negative results on that that appear in one of the papers that I think that I mentioned on the next slide here at towards the end. Where is it? Yeah, the role of neural network activation functions is a very short little article, but it kind of touches on this and explains a bit about what's special about these truncated power functions, which lead to splines in one dimension and generalizations, sort of ridge splines, if you will, in multiple dimensions. And why, if you move away from truncated powers, things don't come out so cleanly. At least we haven't found a nice, clean way to deal with other activations. So that's a super good question, and I hope that was helpful. Annie asked, interpretation of a deep NN, deep neural network is always very challenging. Are there any comments on attention-based neural networks? That's a super good question. No, I don't know that I'm prepared to say anything about how it relates to attention-based neural networks or transformer models or anything like that. Certainly, in those types of models, you will see feed-forward neural network blocks appearing in there. I guess, at least to my limited knowledge of some of those techniques, I think you'll see them some making an appearance somewhere within the overall architectures of those type of methods. So probably this could help understand certain aspects of those in some way, but I haven't thought about it at all. It's another great direction for future work. So I'll leave it to Annie. Maybe she can do it.
Rob, there are a few other questions in the other chat window. So the first question is, your presentation well situates neural network as a statistical penalized optimization procedure that is optimal on the RBVK space. What about uncertainty quantification?
I see. I guess there's so something like confidence intervals were they interested in, or I'm not sure what they have in mind in terms of uncertainty quantification. You would naturally, in this kind of setting, you might sort of say, well, I'm making predictions, or the output of my neural network is making some prediction. How much confidence do I have in that prediction? And I guess there'd be various ways in which some of this might be helpful for that sort of quantification. We've seen that in other areas of nonparametric statistics. I'm sure Flori and Bodhi are familiar with this, but for example, Richard Nicol from Cambridge has worked on things like this in sort of Wavelet and Bezov kind of space methods. So some of that might have analogs here in these RBV settings. So I'm not sure if that's the sort of uncertainty quantification the person had in mind, but I think that's important, obviously, and maybe there would be some utility to these insights that we get from this work for that type of problem of uncertainty quantification.
So Rob, I had a very similar question. Since are the rates of convergence of all these function spaces estimation in these function spaces already worked out?
I would say we know what they are, at least in the single layer case. And so if I could even go back to that, maybe I'll just pop out and go back to this kind of important slide that talked about that a little bit. I think it's like this one here. So because we have, we know these approximation rates here, if you wanted to go through like a metric entropy style argument, you could easily kind of formalize what I have here, right? I guess the open question that is something Rahul and I are working on, again, just for the single layer case, is what about the actual solutions to the variational problem? So if I don't go through metric entropy, and just do a covering kind of argument. But I really say, what about the solution to the variational problem that we're setting out to solve? What can you say about that? Then you probably have to use maybe some techniques like work from Sarah Vandegeer's great M estimation book. I'm pretty sure if you took her book and what we know about these approximation rates and metric entropies, it would all come together nicely, because she has some great work on solutions to these variational types of problems. And so I think this is known, right? Right here, but to really kind of do it carefully and make sure we dot all I's and cross the T's, there's a little bit more work to do. When it comes to the deep spaces and so forth, that I haven't thought about and haven't started on, and I'm not even sure that's totally open as far as I know. And I think it's super interesting. Although I will say again, people like Boris Hannon, Ron DeVore, and others from the approximation theory community have been looking at approximation rates in deep neural network architecture. So that's probably a gateway to start thinking about that. And then just maybe if I could, one other thing I'd like to say about this is when we're training, these are very nonlinear and also non-convexly parameterized models. And so we're just using gradient descent or some variation of it with regularization to train neural networks. So just the question of whether or not those algorithms will converge to solutions of the variational problem is unclear. There's been a huge amount of work in the machine learning community to try to prove things about the convergence of stochastic gradient descent, say, in these non-convex settings. And a lot's known. And empirically, my experience and the experience of the community is that we do tend to find good solutions, but actually certifying that they're truly minimizers of the variational problem is probably going to be difficult, especially in the deeper architectures. Maybe you could say some things under some mild assumptions for single layer shallow neural networks, but yeah, there's a lot of interesting questions surrounding how to solve the variational problem. And going back to the locally adaptive regression splines, if you look at Mammon and Vandegeer, they have some interesting proposals for algorithms of how to do it. Ryan Tibshirani had this lasso formulation, but you could also equivalently solve the locally adaptive regression spline problem using your favorite optimizer from PyTorch, like Atom. And that's what I used when I trained with neural networks. So, and they seem to give great solutions that are just as good as the solutions that you get using something like a L1 regularization lasso technique, which Ryan used, although they might not be as efficient in terms of number of iterations. As we saw, sparsity can really help speed up the conversions algorithmically. So that's a long answer, sorry. Are there other
Thanks,
questions?
Rob. Yeah, there are other questions. Srijita writes, can we learn what is the minimum L in which the function lies in the RBV2L space?
Yeah, that is a fantastic question. I have no idea. Yeah, so, I mean, certainly we could do the usual thing, set up a sequence of nested spaces with increasing L and maybe do some a model selection over a structured set of neural network spaces like that and adaptively choose the right one based on the data. That seems like something you could set up and do, but we don't really know, or at least I don't know, like why would, this gets back to this question of, well, how deep should we go? What does that mean in terms of approximation, localization, and all those things? And this is not something that I understand, and I don't think anybody really has a total understanding of that yet. So it's a great question. I think it probably would be sensible to maybe do some sort of adaptive selection of depth. And people do that, I guess, in neural networks. They do all sorts of optimizations over various architectural structures, including depth. So yeah, I think that's an area that's ripe for further study.
Thanks, Rob. So there's another question by Andrej, who asks, in terms of function spaces, it might be great to generalize also to different complex valued neural network architectures.
So by complex value, does he literally mean complex number valued? Is that what he's saying? Or I'm not sure.
I am not completely sure. Yes, he writes yes.
Yeah, I think that's a very interesting idea. I have to say, I've wondered a little bit, probably the person who's asking the question has thought about more than me, but you might be familiar with ideas in wavelets like the complex wavelet transform or dual wavelet transform that was very popular and very effective because it has more rotational invariance properties once you go to complex numbers. I'm not sure exactly how and why people use complex valued neural networks, but yeah, I think that's an interesting question. Yeah, but I don't know too much about it, so I can't say. But yes, there's certainly a precedent for moving from real valued representations to complex valued representations all the time across signal processing and so forth. So I guess similar things come up in neural networks. So interesting, but I don't know too much about it.
That is all the questions I have from here, I think. Flori, if you have more, you can go ahead.
No, I don't see anything more. No. Perhaps people who have other questions may connect directly with Rob. You can find him. He's perhaps it's a good time to wrap up the session and thank Rob for a fascinating, truly fascinating, beautiful lecture on, as I said, present, past, and most certainly future of deep learning. And we really were honored that you could be with us this afternoon or morning in Seattle.
Yeah.
I was going
to say good day because people are probably tuning in from all over, who knows. But yeah, I really, the pleasure and the honor has been all mine. It's been great. I really appreciate all the great questions that we had afterwards too. I'm glad people enjoyed it. And yeah, I'd be happy to follow up with people via email, and I'll make sure I get my slides up too. So thanks everybody for tuning in, and thanks especially to Bodhi and Flori for managing everything and inviting me and so forth. It's really been great. I have my medal here somewhere. I should have had the picture, but it's great. You get a medallion lecture medal. So that's super cool. Really, really happy and honored to do this. Thank you.
Thank you.
All right. Well, next time, maybe we'll meet in person.
For sure.
Just to make sure, Rob, that you can post your talk on that in the system, and do you want to try that or?
Sure. Yeah. Should I stay on Zoom while we're doing this? I stopped sharing. Let me kind of move around the GSM site. Yep. Well, I'm finding it. Let me take my slides and make a PDF of them to post, because I want to make sure I have the final freshest version to post up there. Export it to PDF. Okay, I'm exporting it to PDF.
I'll let the two of you work it out. Is that
okay?
Yeah. See you guys. Very nice seeing you. Very nice seeing you.
Yeah. Hey, Flori, tell me when your talk's going to be. Send me an email so I can tune in.
I'll follow up via email with both of you.
Awesome.
I'll let you upload the file.
Okay, cool.
See ya.
See ya. Okay, so I'm accessing GSM now. And I'm in. I have my profile and stuff. I'm not sure where I should go in.
Do you see the Medallion Lecture 2?
Yeah, let me go to that agenda Tuesday. Almost there. Where's Medallion? Yeah. Medallion Lecture 2, okay, now I'm there. And files?
Yes, files. Now,
Well,
can
let
you
me-
drop it here or
Yeah,
do
let
so?
me
I'm not
try.
sure how to upload it here.
No, it's kind of coughed at that. Maybe I have to, let me join the meeting again. I don't know. Let me try that. Oh, wait, no, now I'm here. Now I'm,
Rob, in the worst case, you can send the file to me again. I can coordinate with the IMS.
I'm back. I'm back.
No,
Yeah.
okay. No, I was
yeah.
just saying. Anyway, I think in 5 minutes we'll be cut off. So
Yeah.
You can send it to me. I can talk to the ASA authorities and have it posted on these files.
Perfect. That's great. I will email you that now. It'll probably be one of these mail drop types of things, but it should be there.
Yes.
And
Yes.
yeah, perfect.
Thank you.
Good. And then if there's anything else I can do in terms of posting it, or if somebody just says, oh, here's how we should do it, just let me know and I'll do it myself.
Please. Yeah, I'll do that.
Okay.
Thanks, Rob. Thank you.
Yeah,
Thank
terrific.
you. Thank you
That
for an
was a lot of
excellent,
fun.
great talk.
Great questions, things to think about for me too. So I took some notes on some of the questions. I'm going to go back and do some thinking. So thanks to everyone. Okay,
Thanks,
see you.
Bye, everyone. Bye.